Welcome to the first seminar of the winter semester. And it's my pleasure to introduce one of the newest members of our Michigan Control community, Nico Lindsay, who comes here from after a PhD at Berkeley and a postdoc at Caltech. And he works in cyber systems and I'll let him tell.
Thank you so much, Jim. So good afternoon, everyone. I'm delighted to be with you today. Our conversation today is going to be about system level design. So the actual topic is going to be about how can we prove that the systems that we put together by interconnecting pieces will have desired properties. And that's what we mean by this formal system level design, okay, by having assurance that we're going to have desired properties as we build our systems. And the reason we are interested in such a question, of course, is because in the system industries, we tend to have problems. So the frequent news of recalls and recertifications in automotive and aerospace is an eloquent testimony to the difficulty of system design. And we may ask the question, why is such the state of affairs? And one of the reasons why we have this today is because we lack theoretical and practical tools that will ensure that the systems that we obtain by interconnecting pieces will end up in desired properties. Okay? And we see, for example, in the aerospace community, a lot of stress on this concept of digital engineering, right? And as we look for a definition of what is meant by such a concept, we can look, for example, at Terry Hill, who leads the effort of digital engineering at the entire NASA. And that is his definition of digital engineering. So he says that digital engineering is all about making products faster with better schedule, better performance, better everything. How? Through the integration of processes, tools, models, and so on, right? Along with a seamless flow of information, etc. We can find, very similar quotes coming from people in government agencies, in academia, that are calling for the development of a system science. So the point is that in our engineering disciplines, we have excellent tools to design components in isolation. We know our control theory, right, that is going to allow us to design, several blocks and so on. We know about our structures and etc. But today we lack a science of interconnection that will allow us to understand systems and so on. So as we try to think about the requirements that we should have on such a science of interconnection of pieces, we can list several requirements. So to start with, whatever theoretical framework we end up using, it should better be able to allow us to express and manipulate requirements coming from heterogeneous sources. So in complex systems, we are going to have at the table, people coming from both manufacturing and financials. We are going to have legal and certifications. We are going to have performance, safety, security. So we should be able to express and manipulate requirements coming from all these places. Okay, so that's one. The second challenge that we have in the design of complex systems is at the supply chains. Today, there is a significant amount of friction in supply chains. And what happens is system integrators and suppliers enter into a business relationship through the concept of a legal contract. So this notion, right, is something that binds these parties into a business relationship. Now, we can dream about a situation in which these parties, in addition to exchanging this legal object, namely the legal contract, they would also exchange a technical contract whereby the integrator would know a priori that if the supplier implements this contract correctly, this implementation is going to integrate correctly in the system and the system will have desired properties. Okay? So the third challenge that we have today in system design is the heterogeneity of our tools used to prove various parts, various pieces of the cake. So anytime, of course, that when we have structures and thermals, we are going to use a form of finite elements. When we have software in the middle, we are going to be using label transition systems. When we have to do energy transfers between a place and another, we are going to use a form of circuit theory and so on. So at some point, we are going to need to integrate into the system the conclusions that are reached from each of the places, from each of these various analyses. So the question is, how can we do something like that? So here is where contracts are going to play a role. So what are contracts? Contracts are going to be a couple of things. They are both an algebra and a methodology that will enable us to do system level design in two different ways. The first one is by addressing the question of system integration. So what do we mean about system integration is, how do I understand the whole from knowledge of the parts? So in other words, the idea is that we are system integrators receiving pieces from various providers, and we want to understand our system by having knowledge of the parts. Contracts are going to give us an algebraic operation, described soon, and this is going to be called, contract composition. That is going to do that for us. It's going to go from the local to the global. Conversely, contracts are also going to allow us to do the opposite kind of analysis. Namely, suppose that I have a goal for what my system has to do, and I already designed one of the pieces of that system. So the question that I want to answer is, what is the most relaxed specification of the piece that I have to add to my system so that it does what I want it to do? So contracts will have something called quotient that solves that problem optimally. So this pertains to system integration. System integration is all about bringing pieces into a whole. The second aspect of system design is something that we call handling multiple viewpoints. So the notion of viewpoints is the fact that sometimes at the same company, we can have multiple groups working on different aspects of the same object. So we have all seen the cartoon of many people looking at an elephant, and they conclude that it's different things from the angle that they are looking at, right? So at the same, people working on the same object may be focusing on different aspects. So there's a group that can be in charge of generating a functionality specification, another one who generates a power or timing specification, and so on. So the question is, how do you bring this data together into a single specification? And contracts have an algebraic operation called merging that will do that. So throughout this talk, we are going to be looking at these algebraic operations applied to certain examples. And we are also going to be talking about something called PACTI. So PACTI is a tool that was developed over the last couple of years, very much under active development right now, which attempts to bring these algebraic operations, to practice so that we can carry out system-level design in our various disciplines. So if you go to pacti.org, you can see what this is about. Now, PACTI, over the last couple of years, has been applied to carry out system-level design in subjects of cyber-physical systems, which we see on the left-hand side of this slide, and also synthetic biology that we see on the right-hand side. So regarding cyber-physical systems, on the top left, we have an application on space mission design, in collaboration with NASA JPL. And we also have applications to self-driving cars, multi-agent systems, and so on. And on the synthetic biology side of things, the kinds of use that we have found that contracts have been a good tool to be applied to is when we design circuits inside of bacteria, right? We can characterize circuits working independently, but the problem is that when these two circuits are implemented on the same cell, they compete for resources, and this resource competition ends up in very different behaviors than when they were implemented separately, and so on. So the question is, can we use contracts in order to characterize these interactions and so on? And this has been the application there. So, okay, that being said, this is more or less our progression of topics for the discussion. So in order to introduce contracts and to see where we may need something else regarding the set of tools that we have today, we are going to be talking first about an application led by NASA JPL on space mission design. So this is going to introduce a couple of algebraic operations. Then we are going to look at autonomous driving. Then we are going to, actually let's define the mathematics that we are using here. And then we'll talk about some future work and so on. So to get started, we are going to focus on this space mission design. So we are going to consider what do we want to do, and then why might we need to be using these kinds of tools. So the setup looks like this. So suppose that we want to build a spacecraft in order to complete what is called a rendezvous mission. So rendezvous mission means we are shipping the spacecraft from Earth, and the objective is to go meet some object of scientific interest somewhere in space. So this is going to be an asteroid or something that our science friends are telling us we care about. Right? So the way in which we can understand this spacecraft is as an object that at any given point in time is going to be doing one out of four possible things. So the spacecraft may be in DSN mode. So DSN stands for Deep Space Network. That means if you are the spacecraft, you look at Earth and you exchange data with Earth. So DSN, this is the communication technology that NASA uses to talk to spacecraft. The spacecraft may also be in SBO mode. That means small body object. It means you look at the object that you are supposed to study and you deploy your scientific instrumentation to get data from that object. TCM stands for trajectory correction maneuvering. So that means engage your actuation in order to approach the object that we are supposed to study. Finally, charging means look at the sun and get maximum energy from this object. So the question that JPL posed at this point was extremely high level. Right? So they said, suppose that we get from something like a scheduler a sequence of these tasks. So somebody tells us first we are going to to charge, then we communicate with Earth, then we do SBO and so on. So we get a fixed plan that has a lot of these tasks in a sequence. Say for example 80 or 100. Now there are two high-level questions that we would like to address. The first one is, can we complete this schedule while making sure that our charge is going to remain above a certain threshold, throughout the entire mission? In other words, we do not want to lose access to this object, of course, during its operation. The second question is, can this spacecraft record and transmit to Earth all the measurements, all the data that we wish to gather from this asteroid or this object of scientific interest? Okay, so two very high-level questions that we have at this point. Now, what our colleagues from JPL tell us is that at this point, we want to avoid using simulation models for a few reasons. Now, simulation models, remember, are really the workhorse of engineering analysis, but we want to avoid them for a few reasons. The first is we are so early in the design process that simulation models may not be available at all, right? They just have not been developed yet. So second reason is detailed simulation models are accessible only to about 3 people in our organization. So if you think about a detailed simulation model for your structures or for your fluid dynamics and so on, there are a few people that are going to have the deep expertise needed to make conclusions based on those objects. The third one is the fact that detailed simulations usually require extensive hardware and software setup. So, and they only yield insight into carefully controlled, trajectories that we set for our analysis. Forget about putting together a simulation for the entire system and so on. So, considering these things, we don't even have them, and they give us limited insight into all the various operating conditions. We want to use something else, and as you can imagine, we are going to be using contracts. So let's start talking about contracts for a couple of seconds. Okay, actually, even before we get there, so JPL tells us this. At this point in the design process, we would be, if we're working for them, we are going to take a look at what is called the Systems Engineering Handbook by NASA. So the handbook tells us that, with the kinds of questions that we have, we are in the very early stages of the design process, right? What we have are the two high-level questions of, we want to gather this amount of data from our from this asteroid, the small body object, and then what we are going to be doing next, working for them, is going to engage with all the stakeholders involved in this particular mission in order to take these high-level requirements and refine them into detailed requirements for each of the pieces of the design. Okay, so what they tell us typically is that this design process can involve very deep feedback loops, in the sense that in order to take the high-level requirements into the detailed requirements, extensive analysis is usually performed and so on. And then sometimes we figure out that there is a problem after we have carried out the decomposition, and we have to go all the way back. Okay, so part of the motivation, to carry out this analysis is to say, can we do something involving much shallower feedback loops in such a way that we can do, this analysis? And, this is one of the reasons we want to be avoiding the simulation models and using something else being our contracts. So now, what are these objects that we are discussing? So we are going to be representing, right, the components in the system using these objects called assumed guarantee contracts. Contracts are formal specifications. So formal specifications means specifications that a computer can understand. Okay, so a temperature being within a certain bound is something perfectly understandable by a machine. A piece of text, less so. Okay, so specifications having mathematical meaning, but these specifications coming in a specific form. So a contract is going to tell us two things. It's going to say what a certain component does. We call that the guarantees of the contract. And it also states what are the assumptions that this object makes on its context of operation in order for it to be able to deliver its guarantees. Okay? So in other words, a contract is the mathematical analog of a datasheet. So a datasheet for a component will always tell you this is what it does, provided that you give it certain things. So a contract is going to be a pair, assumptions, comma, guarantees. So we see it on the top right of the slide. And an example of that, for example, in a self-driving car application would look like this. So suppose that you want to say something like, okay, I am going to guarantee that my vehicle is going to make it to its destination with a probability of 1 minus epsilon. So, and you can say, I can do that under the assumption that it must so much, 30% of my location sensors are under attack, for example. This will be a valid contract for a security application, right? That for our card. So contracts are useful not only because they allow us to express specifications of components, but because they allow us to manipulate those specifications and therefore do analysis based on them. So to start with, contracts have a notion of order. So we know when a contract is more difficult to implement than another. We'll be more careful about defining that soon. And the second thing that we have with contracts is that they have a rich set of algebraic operations that allow us to do system-level analysis without using the simulation models, only using the contracts. And we're going to be using two for this space mission case study. The first one is about building systems. So when we think about building systems, what we have in mind is this. We understand a system as an interconnection of pieces, like we have in this example, right? So here we have 3 pieces, each of them having its own inputs and outputs. I sub k output is going to be O sub k. And each object comes with its own contract. Each object tells you, this is what I guarantee, provided that you meet my assumptions A sub k. Okay? So we want to go from a diagram that looks like that to a diagram that looks like this, using composition. So we want to somehow manipulate assumptions and guarantees of these objects, okay, in order to be able to draw a box around this structure in such a way that we have top-level inputs I1, I2, top-level output Y, and our objective will be, how do we compute that A parallel, G parallel, which is the system-level specification, okay? So composition is an algebraic operation that goes from the pieces to the system. The second operation that we will use in this analysis is something that we call merging viewpoints. So the situation here looks like this. The outer box that we have in this diagram represents one component in our design. So whatever is a component, right, in our application. And the two contracts that we have internally represent different aspects of that design. So you have a contract for power, you have another contract for functionality, another contract for stability, whatever are our concerns. So the question here is, how can we take that data and generate a single contract for my component? The reason this is useful is because of specification capture. We are familiar from computer science and programming that as we write our routines in a compact way, error tends to be less probable. So the idea here is that if we write our specifications piecemeal by focusing on various aspects independently, then we can use the algebra in order to bring all this together and so on. So to make sure we are on the same page, let's take a look at a couple of examples of these operations. So the first one is going to be on composition, okay? Suppose we have a system that looks like that. So we have 2 objects connected, according to that topology with those inputs and outputs. So we have component M with input out, output O, M prime has input O and output O prime. We are going to assign contracts to these 2 components. So contract C is a contract for M, and C prime is a contract for M prime, okay? So for M, we are saying, as long as my input is bounded by 2, I promise to you that my output is equal to my input. And the second component says, as long as my input is bounded by 1, I promise to you that my output is equal to my input, okay? So that's our exercise. We have 2 components with those specifications. Suppose that we build such a system and we provide it to a third party for use. What would be the specification that we would write for such a system? Is the question well posed? So notice that we said we have 2 objects having those contract specifications. You build it, you give it to your friend. What would you say that to that person is the specification of the resulting system? Any takes on that question? What would be your assumption, for example? Actually, even before we get to the assumption, what are your input and output variables in the specification? Okay, so we heard I and O dash. So why not O? It's an internal variable. The user, we want to draw a box around the entire structure, right? So we don't even get to see O. So what is your assumption for the system specification? Yes.
I must be bounded by 1.
Okay, so I is bounded by 1. Why do you want I to be bounded by 1 and not to be bounded by 2, as we have it there?
Because if it's greater than 1 but less than or equal to 2, then the second contract it wouldn't meet the
Right. then we have problems, right? So we are converging to something that looks like this, right? So we're saying, you know, as long as my input is bounded by 1, my O prime is going to be equal to my input. So, you know, this completely agree, right? The reason we didn't want the input to exceed the value 1 is because the second object, you know, we have no guarantees, right? So presumably we add components to our system because we want them to do something. And the only way in which we can rely on them doing something, right, is if we satisfy their assumptions. So, you know, and then the second virtue that we have in this resulting specification is that O is not mentioned. And again, O, you know, is something that the user is not interested in because, you know, this is going to be an internal variable. So great. So this is what composition does for us. If we use PACTI, the tool that we discussed before, you know, we can actually compute, you know, something like this. So in this software, in lines 1 through 5 that you see you know, on the slide right now, we are instantiating the first contract. So you see that we are saying, you know, here's a contract with an input I, output O, assumptions, input bounded by 2, and, you know, guarantees, whatever is that guarantee, right? Now, then we're doing the same thing for C prime in lines 8 to 12. And in line 15, we're saying, give me the specification of the system resulting by interconnecting these two pieces. And then we are using this composition operation, and what we get is, you know, what we intuited should be the answer in this case. So this is a way, right, in which we can design like using Lego blocks. Notice that implementation details are not used. We are not using simulation models of anything, just our knowledge of the interface specifications. So, okay. So let's consider a slight variation of this now. So composition allows us to get system level specifications. Suppose we have the exact same topology as now, but we slightly change the specifications. So now we say, you know, C prime is the same as before. Input less than 1 gives me this. But the first component says, as long as my input is less than 2, the only thing that I promise is that my output is going to be bounded by 3. Again, same exercise. We build this, we give it to a third, you know, we give it to a friend for use. What is the specification? You know, we can tell that person is obeyed by our system. We don't have to think at this point, right? In the sense that, you know, we can again call PACTI, the tool that we discussed before, and ask the question. So we can define the two contracts for, you know, our two components. We can ask for the composition, and in this case, what we get is an error. And what the error is saying in this example is the following. Remember that the specification that we want for the system should not mention the variable O, because as we discussed, the user doesn't care about the internal variable O, right? We want to give a specification at the interfaces. The complaint that we are getting from the tool right now is that I cannot get rid of that variable O. And to me, it was remarkable that, you know, the fact that we have a logical impossibility to eliminate variable O, in fact, means that we may have a bug in our design. And the bug in this case is that, you know, this guarantee cannot be used in order to satisfy the assumption of the next object, right? So in this system, you know, we can be sending 3 volts or 3, you know, whatever are the units of our design, into a design that is asking for a maximum of 1. If this were electronics, we may be frying a component and so on. Something that I like to stress to some of our colleagues from industry is that this is not the kind of bug that we are guaranteed to catch in simulation. In simulation, it could have been the case that O was 0. So if O was 0, the guarantees are happy, the assumptions of the next guy are happy, right? So, you know, so we get the idea, right, about this, right? So simulation is not guaranteed to catch this. In simulation, we have to be creative regarding the traces that we use to stimulate our designs in such a way that, you know, we try to hit the corners. But here we don't have to, come up with that kind of creative notions. Yes.
So, bug, or is it just that there are no assumptions in the guarantees?
Okay.
Isn't the empty set, isn't that a valid contract?
Okay, so the question is, you know, do we always need to interpret this as a bug or something like that? So not necessarily, right? So
Because it seems to me that those two things combined just mean I can't assume anything and I can't guarantee anything.
right. So I agree with that statement. So in the sense that it is application dependent, right? So if we had implemented this in electronics or something like that, you know, then we may have a bug in front of us. But this is definitely application dependent. What this is telling us is that there is. In this example, what happened was that we were able to generate a constraint on the top level input, which is this, that would make sure that the second object keeps its guarantees within the assumptions of the next guy. We are not able to do that here, right? So it is how to interpret, this result, definitely depends on the application. But the point is that, we can use this as a diagnostics tool about the validity of our designs. Okay. Yes.
So for the contract, the first contract, even if the guarantee of the first contract is, let's say, the O is bounded within 1 by 1, it means the assumption of the second contract, the system cannot still, not get rid of O in the whole system, right?
Yes, you can. Yes, you can. If this is less than 1,
Yeah.
then you can eliminate the internal variable O.
What's the final guarantee for the system?
The-
O prime is equal to O, but you get rid of O in the final guarantee.
Oh, I agree with that. I meant the assumptions are satisfied. Indeed. Okay, I agree with your point. So in the sense that the assumptions are satisfied, the assumptions are going to be, the assumption of the system level contract will be, if your top level input is less than 2, we are going to have this elimination error at the level of the guarantees. What happened in this problem is that this elimination error happened at the level of the assumptions. In that case, it will be at the level of the guarantees.
So whenever PACT throws up an compilation error, do I say that there is something wrong with my simulations, or do I say that there is something wrong with my assumptions? What do I do when a compilation error is thrown?
Okay, so if we get an error of this form, so what this is telling us is that there is a problem with your O. Right here, right? So what we know is that our variable actually, this is telling us that that there are 2 variables. We can refine that further. PACT can tell you, exactly what variable is the one that it has trouble with. And at this point, in the implementation, let's see, it will be the user's responsibility to to look at the constraints that generated that. But that is just how things are now. We can further refine that. Yes.
Sorry to belabor this one.
Yes.
So, if components have costs, non-zero costs, are there situations in which you would ever do this instead of just putting nothing in? So the question came up, is this a bug or not?
Okay.
But if components have some cost, you could have achieved the same thing by just putting nothing in, which would have a lower cost. So are there situations in which it would ever make sense to put in something where you can't guarantee anything or you can't meet your assumption?
Okay, so in that case, I would say that it depends whether what kind of objects we are using in our system would depend on what is our top level specification. So for example, if our top level specification in the system was make sure that O prime is equal to I, then in the second implementation, we would not be able to achieve that. So we would need to place the second component, right? So let's see. So the number of components that we add depends, of course, on the top level specification that we have at hand, right? And we will be able to catch the differences using contract composition. Does that address?
So in the case where, so the second example that you had.
Right.
Isn't the second example equivalent to just not putting in those components at all? Don't you get the same effect?
In that case, if we said something like, I don't need any guarantees, for example, then sure.
But I can't get any guarantees
Right.
if I put these 2 components in.
Exactly. I mean, the point about this, right, is to show that that this analysis can be used, in order to detect these interconnection problems. Right? I mean, now the question, am I meeting my goals, is orthogonal. It's actually checked using contract refinement. Okay. Yes. So okay. So then, armed with these 2 tools, then we're going to reconsider our case study. So remember, the case study is all about. Let's see, is this space mission? We have these different modes of operation. And the idea is to, if someone gives me a sequence of these objects, can I answer these 2 questions? Let's answer these 2 questions. Can we complete this without our charge falling below a threshold? And can we record and transmit, all the observations? So the way that JPL approached this was as follows. So they said, the system that we are going to consider is going to be the sequence of tasks that we have in the schedule. So each task is going to itself be a component in of my analysis. Notice that this is a very interesting notion of a system, right? So now the mission becomes the system. Now, throughout the evolution of this mission, they said we are going to care about certain quantities of interest. We could call them state, but we avoid the word because it conflicts with something else, right? So these quantities of interest that we are going to care about are going to be what is the value of my charge, right, at any given time, what is the amount of data that we have gathered, from our asteroid? How much data have we sent to Earth, and how close are we to the object that we are supposed to study? You can immediately notice that, for example, if you want to make measurements of the asteroid that we are interested in, we need to have an assumption on how close we are, right? So we cannot make use of our instrumentation if we are very far away. Similarly, if we are going to do something like trajectory correction maneuver, warming up our fuel and all of that, that's going to take power. So we need to have an assumption on how much charge we have available. So which means that at some point you're going to need to charge again, and so on. So we're going to have assumptions and guarantees on all of these objects. So the way they go about this is about generating contracts for each of these tasks is as follows. So what JPL does is, for every one of the tasks that they are going to have in this mission, they generate an object that looks like this squared label A right there. So A is going to be one viewpoint for each task that we have in our mission. Notice that we have two input variables. There is something called V initial, and there is a delta T. V initial is going to correspond to the value of your quantity of interest when we begin executing that mode of operation. So when we begin charging, what is currently the state of my charge in the battery? Delta T corresponds to the amount of time during which we are going to be executing that particular mode of operation. And V out is going to be the value of the quantity of interest after we are done executing that mode of operation. So their contracts look like this. So on the y-axis, we have our quantity of interest, and on the x-axis, we have the delta T. When delta T is equal to 0, just sitting on the y-axis, we actually make an assumption on the value of our quantity of interest, right? So this is what is given to us right at the when we begin executing the mode of operation. When delta T is different from 0, then we are going to have we're going to be given a guarantee on what is going to be the value, or what are the bounds on the quantity of interest after a certain amount of time. Notice that we have affine bounds on these quantities of interest. That doesn't mean that we have, of course, linear dynamics. The dynamics can be as non-linear as we want, but we are bounding them using these affine expressions. So, okay, so that gives us what we can call the atomic contracts. Remember, we have one of these for each of the quantities of interest, also called viewpoints. We have one of these for power, one of these for scientific data gathering, and so on, which is the figure that we have here. So every task gives us access to one of these contracts for power, one for scientific data gathering, one for how close we are to our object. We use the operation of contract merging in order to generate a single contract for that task, okay? So now we know what charging does to each of my quantities of interest, to power, to scientific data gathering, and so on. So the next step that JPL does is the following. So they said, give me any spacecraft that I have specified. Now we have a contract for each of the modes of operation of the spacecraft. Because what we have is a chain of these objects given to us by a scheduler, now we can compose all of this in order to get a specification for the entire mission. And remember that using contract composition, we have two possible outcomes. Either it works or it doesn't. When it doesn't, it means that there exists some task somewhere in the sequence whose assumptions we are not guaranteed to satisfy, okay? So exactly as our example of diagnostics and stuff like that, came up before. Again, now that we have, 40 of these, 50 of these, coming up with a simulation that eventually is going to fail will be extremely difficult. But because we are here operating directly on the specifications, here we can find a condition, right, that is going to, let's see, make one of the components not have its assumption satisfied. When it works, however, when we get a positive, when we get a result out of this composition, we are guaranteed. So we have the theorem that if we implement each of the tasks correctly, or as we said we would in our contracts, then the system is going to satisfy the resulting contract, and our desired performance is going to be satisfied. So the result is very satisfying in the sense that we actually have a proof that this is going to work, provided that the pieces are implemented correctly. So this is the kind of analysis that JPL carried out. And something that they did next was to say, well, but how fast is this? Remember that one of the ways in which we wanted to use this analysis was in design space exploration. So we wanted to try various spacecraft configurations and iterate over them and focus on the ones that look more promising, right? So this kind of analysis on 200 different spacecraft with schedules of length, 80 and 100, took about between 1 and 2 minutes of execution time. So you can see that, this is quite tractable from the perspective of design space exploration and so on. And this is, okay, these are some additional results, but the point of this example is to say that, that we seem to be approaching this shallower feedback loop that we were after, by using not simulation models, but by using these contract specifications for all the pieces. So, okay, what we do next now is to consider a different example that uses a different operation. Yes, please.
Just have one question. You're operating at the level of contract, so it's like velocities and energy charge. How do you connect that to like the spacecraft configurations? That's the piece that I'm missing. So when you said they were studying 100 different spacecraft configurations, how are they mapping those configurations to what the contracts are saying, which are at some level of abstraction?
Exactly. That is in here. So remember that we are considering for each spacecraft, we are generating in the end 4 contracts, 1 for each of the modes of operation. Let's talk about DSN. DSN is the Deep Space Network. This is the communication. So a given spacecraft is going to have a particular contract for its communication capabilities. So that's the way in which the specifics of the spacecraft are being reflected on the contract that we write for it. Similarly, when we talk about the charging contract, the technologies that we used for battery charging and for battery storage and so on are going to be reflected in the actual specifications that we have for that particular spacecraft. That's what we mean by trying different configurations. So it means I have multiple technologies for doing these tasks. So, and we are mixing and matching in order to build the various spacecraft. Okay. Yeah. So, okay. So in the next example, yes.
Question. So is it easy to go from physics to these contracts? Is it learned? Is it like some closed form computation? Or is it like if I give you the complex simulation model, can you go to the contracts from simulation model?
Yes. In general, to that question, I would say that is a research question. And this is something that will need to be addressed in every field in which these methodologies and techniques are used. So the way that I see contracts is as very basic building blocks. It's almost like linear algebra. So how we use them and how we use their operations and so on really depends on our applications. The way in which we generate the contracts for this space mission case study was really developed by experts. So somebody said, okay, this is more or less what I can give you or what this spacecraft is going to give us and so on. But absolutely, I mean, generating, okay, actually the one that we are going to be looking in the next example about autonomous driving, we generate those contracts from simulation and from formal methods and from statistical model checking. So yes, so how we generate them, I think it's really application dependent. Yeah. So, okay. So in this first example, right, we took a look at 2 contract operations, composition and merging. Now we are in this other case study, we're going to be using something else. So the application that we have in mind, looks like this. So there is a self-driving car that we are trying to design, and the situation that we consider is the following: the car is approaching a crosswalk, and at this crosswalk, we can have 1 out of 3 situations. The crosswalk may have a pedestrian on it. The crosswalk may have a box, may have something that is not a pedestrian, or it may be empty. And the high-level question that we want to address is, what should be the specification of our perception capability inside of this car? And I'll say more about that in a couple of slides. Okay, but the general question will be, how much how demanding should we be on our object recognition capabilities on this car? And for that, we are going to be using contracts. So this is going to be the algebraic tool that we will use. Remember that what we have used now is this notion of building systems and contract composition. We know how to go from pieces, from the pieces to the whole. Now, what we will do now is the opposite. Suppose now that we have a system given by the outer box, and this system has this specification ASGS, so A system, G system, right? And inside of that object, there is a piece that we already developed. So, we want to design a car with a given specification, and we already developed the engine. What we want to find is, what is the missing part that we have to add to the car so that these 2 objects in composition refine my top-level specification. And this is given in optimal form by something called the contract quotient. So the contract quotient is going to identify this assumption quotient guarantee Q such that this is solved optimally, okay? So the quotient is about finding these missing pieces in the designs. So let's go back to the example that we were considering. There's a car approaching a crosswalk, and there may be somebody in that crosswalk, okay? We are going to understand the car as the interconnection of two pieces. There is going to be a perception piece, and there is going to be a controller, okay? So the perception, of course, recognizes objects based on images, and the controller is going to make the vehicle take actions. So the high-level question that we have is, what should be the specification of the perception component? Typically, the way that the formal methods community has approached the question of how should we specify perception components is by saying this. We do not have, right, a closed form mathematical expression that tells me what an ideal pedestrian is. So what we tend to use are, detection rates, meaning that, okay, if the perception component tells me that there's a pedestrian, how much do I trust it? There's a 80% probability, right, that it is detecting the right object, and so on. Now, one question that we have generally is, how much is good enough for a perception component? If I am detecting pedestrians, do I really need 99 with a lot of 9%, or are we okay with 60? That's not obvious how to answer that question. Something that is a little closer, to us is the notion of safety for the entire system. So many times it is considerably easier to specify the system than to specify the internal parts. For example, in the case of vehicles, there are certification authorities that are going to tell us, this has to be your probability of being safe. Usually the way in which that comes is by saying that, okay, you can have, one failure for every so many hours of operation or every so many miles of driving and so on, right? So this is the specification that we write for the system. We write a specification that talks about the probability of our car being safe. That's what we encode in this symbol phi that we see here, in a relationship with the visibility and the environment. So the contract that we write for the system looks like this. So it says, when the visibility is very high, we are going to require our system to be extremely safe, right? And as the visibility degrades, that probability of satisfaction can also degrade, gracefully. But we are going, of course, to place an assumption on the visibility in such a way that, if the visibility is too low, just stop and, wait, right, so that you can operate safely. So this is going to be the specification for the entire system. The situation that we have is a little more complex simply because, we have 3 different controllers, one for each of the situations that we described before. But the specifications that we have for the controllers are going to be of a similar flavor. Each controller is going to give a guarantee on the probability that it can be safe in a relation with the detection rate of the perception component. In other words, if the perception is always right on target, telling the truth, then we are going to require the controller to be super safe. And we can degrade that, of course, as the detection rate falls, so on. So, to make the long story short, the situation that we have looks like this now. We have a specification for the system, and we have specifications for some constituent elements of our system, which is the 3 controllers. Using the 2 algebraic operations that we developed until now, we can summarize this into a single specification for the system using merging, and a single controller specification using the composition of those 3 objects. And the situation in which we are now is this. We have a system specification, we have a controller specification. We want to figure out what is the specification of this missing object. And this is exactly where the quotient comes in. So we have the diagram. The quotient gives us the most relaxed specification for perception, and it looks something like this, right? So what we end up computing says, this is going to be your detection rate in a relationship with the visibility. So if the visibility is very high, we are going to require perception to be right on target. Otherwise, it can degrade and so on. On the website, we discussed before, pacti.org, we have all the code and the details of this example. But there are a couple of comments that are good to note about this. The first one is that, in the design methodology that we are considering right now, at this point, we can do the following. After we have computed this contract for the perception component, we, the system integrators, can provide this contract to a perception expert, and we are guaranteed that if the perception expert implements it correctly, this implementation is going to make our system work, okay? So that's a very attractive property of this. The second one is that we, as the system integrators, do not need to give the perception expert any information about our system except this perception specification. We do not have to provide any trade secrets, anything else about the system. So that definitely helps the system integrator, but it also helps the perception expert because that person is now not going to be distracted by anything that is not directly relevant to the perception component. So this is a way in which we use quotient to address this application. So, okay, now that we have seen, okay, these algebraic operations at work, so there are going to be a couple of slides on what are the actual mathematics of this. So what makes this work and so on, okay? So this is going to be brief on this subject. The actual definition of contracts looks like this. The starting point in order to define contracts mathematically is the notion of a language of specifications. So we start with our basic object being a Boolean algebra B. So the reason this is a Boolean algebra is because the requirements that we express are objects that we conjoin, right? We say things like I need this and this are objects that we disjoin. You can give me this or this and so on. So that is the Boolean algebra aspect of this. But think about this B as being the language that I use, right, in order to express what I need my system to do. So this is, if you want privacy, if you want security specifications, right, this is going to change your B, right? So if you start with that B, then the contract algebra defined over that language is defined in this way. So the contract algebra is going to give us the pairs A, G, where the A, of course, is the assumption, the G is the guarantee. The A and the G are elements of the Boolean algebra, and they satisfy the constraint that we see on the right-hand side of that expression. That constraint is there in order to give assume guarantee semantics to the pair A, G. So in other words, notice what happens when the A is equal to 0. When A is equal to 0, that forces G to be 1. Right? So what that means is think about a legal context of a contract. If somebody doesn't meet your assumptions, you are not liable. So which means that whatever you do is okay. Whatever you do, you are satisfying your guarantees. So that's what that is doing. Okay? So satisfying that. Now, contracts have a notion of order, as we discussed before. So this allows us to compare specifications to each other. We say that a pair A, G is less than a pair A prime, G prime. In other words, that this guy is harder to implement or is a more demanding specification than this one. When two things happen, the G of the more demanding specification is simply harder than the G of the less demanding specification. Say, for example, somebody tells you to implement an amplifier with a tolerance of 1% and somebody else with a 0.1%. One of them is clearly more difficult than the other, right? Because you have your tolerance being tighter. And the assumptions work the other way around. And the reason that happens, think about it this way. Suppose that someone gives you the exact same task to do, but one of them tells you you have to do the same thing, but for a much wider set of environments. So, you have to maintain a 1% tolerance, but now over a temperature range that is 3 times wider. That's harder. Right? So this is the reason that, if your guarantees get harder or your assumptions get bigger, you end up being a more difficult task. So that is the notion of order for contracts. One more definition that follows from this. So there is one operation on contracts, which is usually called the reciprocal or the mirror, that takes a pair A, G and just flips it. The reason this is this operation really works a lot like a negation in Boolean algebra. It ties together a lot of the concepts. And the way that it does that is because it defines a notion of duality for binary operations on the contracts. So duality means this. If we have two binary operations on contracts, like composition and merging, for example, we say that these operations are duals of each other when you can get the reciprocal of one by applying the other operation to the reciprocals of each of the two contracts that you are operating on. So this should remind us of the Morgan's rules, right, in Boolean algebra, right? In the Morgan's rules, like a negation flips the and with the or and so on, right? So this is just generalizing that a bit. So what happens next is, I would say, a miracle in the following sense. Just from the definition that we have now of the contract, without the inclusion of any external axiom, we have an entire set of binary operations of contracts that enable system-level design in the following way. The notion of order that we just introduced generates the operation of disjunction by least upper bound, okay? So that's not axiom, that's a theorem or a proposition. We could speak more about what these operations are used for, but we have a limited time now. So by duality, we get conjunction out of disjunction. So conjunction, okay, this is kind of the logical side of contracts. By using the concept of tensor product in commutative algebra, we get the operation of merging that we used before. The dual of merging happens to be one of our favorite operations, right? Composition that connects the local with the global. So these are all the what I tend to think as the constructive operations on contracts. What happens next is by using the concept of adjoints in category theory, we obtain these operations, which are the ones that undo whatever is going on the left-hand side. So remember, composition builds, quotient takes things apart. And every one of these operations happens to have an adjoint. So merging has separation, conjunction has implication, and so on. So all of these operations are generated, notice this, all of these operations are generated from the definition of contracts, which contains in itself the order. So I say this because the mathematics of contracts are extremely self-contained. You only need the definition, and the definition generates everything on its own. So that of course, usually is connected with this notion of the simplicity is fairly attractive, right? In a theory. So the expressions that we have right now on this slide are, how can we actually, what are the closed forms of all these expressions? And I put this in my PhD thesis a couple of years ago. And something that we have also learned recently is an answer to the following question. So we have these contracts that seem to be pretty useful for engineering and CS and so on. But the question is, are these mathematical objects like some sort of random ad hoc construction, or are they in some sense the only thing they can possibly be, right? Are they in some sense canonical? And we learned that yes, that contracts, using a notion of category theory called adjoint functors, are the unique object that is the left adjoint of something called a closure functor. So this also gives contracts this canonicity aspect to them. This is an ad actually for graduate students here. The mathematics of this are going to be covered in this course next semester. So if this sounds interesting, this is a way to learn more about it. Okay, so applications of this. Let me go to conclusions at this point because let's see, we are rather long time. So right, summary of what we have discussed right now. What do we gain, right, with this assumed guarantee contracts and so on? We can think about systems and subsystems in terms of specification of their specifications, right? Not their implementation details. So the result of that is that the conclusions that we reach are valid as long as we have correct implementations of each of the pieces. So now we are really operating on sets of designs at once. Now, the second aspect is that contracts make assumptions, first-class elements of the theory. In our experience, operating on assumptions is considerably less intuitive than operating on guarantees. So it's very easy to think of guarantees in the sense that, okay, this gives me this gives me that, and I build something. But even when we look at a hello world, level example of contracts, assumptions get pretty confusing. So this is another benefit that we have. Something that we have noticed too is that assumed guarantee reasoning allows us to really scale, a compositional design as we saw in the JPL case study. But something else to say about contracts, okay, is that contracts are here not to replace anything, but to complement the existing theories that we have, in the sense that contracts give us the logical stitching to bring the information about our components into the global view, right? To conclude the system level properties from them. However, when it comes to the point of proving that a local component is stable, we are going to use the tools that we know from control. To prove that it is secure, we are going to use information flow and so on. And you get the point, right? We are going to use the tools from our disciplines in order to prove the local properties. However, now, your local properties of stability or structural analysis and stuff like that you want to add to your components are all encoded in a contract that we can use to do this analysis. So we have discussed work with done with a wonderful team of collaborators and funded by people that very grateful for. So thank you to them. And then right. So thank you so much for your attention. So.
questions?
And very nice talking to you. I think I have a question about quotients, and it might be embedded in the example that you used, which was about perception and control. What comes to mind for me is active perception. The way you control will perhaps influence the visibility. Your visibility is better if you get closer, that kind of thing. So is that what I have in mind, a feedback loop? And not covered, or is it already covered?
Right, right. In the example that we considered, so thanks very much, Brent, for the question. The question was, what is the relationship between, okay, what we discussed right now and feedback situations, right? A specific example of that is going to be something like, when your controller influences perception by changing the environment in which you are in. Indeed, the relationship between assumed guarantee reasoning and feedback is subtle in the following sense. So imagine that you have a single component, okay, that says something like this. As long as my input is less than 1, I promise that my output is equal to 0, okay? So just that, if my input is less than 1, my output is going to be equal to 0. Make a feedback loop out of that. What is the value of your signals, right? So you can say, well, it's going to be 0. That's a valid option, but it can also be anything larger than 1. In this situation. So that shows that feedback and logic definitely need to be addressed with care. We have some applications in which we have done exactly what you're pointing out right now, and we are brainstorming some of them. That being said, this is also an area of existing work and in which more research will be needed, but absolutely important and on the table.
Questions about like dynamic contracts. The contracts that you gave in the examples are like almost static point-wise in time. If this happens, then this will happen at maybe each point in time. But things could be coupled across time and there's memory involved. And so how does that get handled in the framework? If there's time evolutions, this signal satisfies something, maybe that's just naturally in the contract or not.
Right. So there are two ways of looking at that, right? So in the case of, okay, so to preface the discussion on that, what I would say is that contracts themselves, the definition that we had from the mathematical object and so on, are indifferent to the way in which we express the specifications, right? So that was embedded in our Boolean algebra B and so on. The contracts that we wrote in the case of the space mission application, remember that they had a parameter delta T. And this parameter delta T, right, allowed us to speak about, okay, how long is something varying and so on. And that was an input variable to the contract. The contract itself, didn't even know that this represented time, right? For the contract, this was something of meaning to the user and so on. So this is a way in which, at this point, they have addressed that particular timing situation. So now, something that changes over time, something that comes to mind, let's see, of a potential application is something like MPC, right? So you are doing something. When doing MPC, we tend to relinearize, our systems around, the location in which we are operating at any given point, right? We could also imagine, recomputing a contract, according to the operating point in which we are at any given point, according to the if the technology that we have now for contract processing depends, for example, on something like affine bounds, which is what we are doing right now. So, what I'm saying is that I can see some ways, of addressing this, but again, this is also application dependent. And this is something also that I would like to stress in general, that this is fairly new, right? So I am sure that whatever new application area that, that we start discussing is going to itself generate questions that will both influence the contracts and they will also do something to the application. So I only have a partial answer, to that, and I'm sure there are things that are not known. Yes.
But I didn't get when you find the order over the assumed guarantee space, you have like orders over the guarantees themselves. And I think you got the intuitive idea if you want something to hold for a longer period of time, it's a harder guarantee or a harder contract or assumption. But how did you define that over your Boolean algebra? Is there like is there a formal way, or is it like application dependent?
Yes, exactly. So you're referring to this, but you're referring to this, and then what this is saying is that this is really defining this symbol right here, right? We're saying, okay, this is less than this when we have this and we have this. So your point is, how do you define that object right there, right? So how can you actually compare two specifications? So think about the notion of, okay, I have let's see, I have a temperature range, right, in between 0 and 100 degrees C, right? And then I have another temperature range, which is more limited, like, 10 and 30, between 10 and 30 or something like that. In that case, you have a subset relationship and so on. So that tends to give rise to the partial order. But even independent of that, so in this definition, this symbol is defined by your Boolean algebra B. So this is already coming from your language, right? So you got to define it even before you speak about contracts. We are using that order in order to define the order on contracts. Okay. Yes.
One more question.
This may be a naive question, but I'm thinking, that I guess there are other ways besides contracts to specify system behavior. One, have you encountered a situation where you specify a system behavior and back out what the contracts are that are equivalent to that, and find out that the number of contracts you need is countably infinite?
Let me make sure I understand your question. Your question is,
Can you always characterize system behavior by a finite number of contracts? Or are there situations where you actually need infinite contracts to get something, some kind of?
Okay. So the question is, are there situations when you need infinite contracts in order to characterize something? Let's see, we can build one on the spot, right? So in the sense that, say for example, let's think about the trajectories, that the spacecraft would follow. If we use these contracts given by a language of affine bounds, and then you say, well, let me write a contract for every possible point that I have right here, right? So then, then you could say, I have an infinite number of contracts in order to do that. But what I think, the way in which we typically address this, right, is by going to each application area and asking ourselves the question, what is the way? Actually, okay. There are two questions that we typically ask. Suppose that we have a new application area, we want to use this kind of contract level analysis. The first question that we ask ourselves is, what is the question that we want to answer regarding our system, right? So you tell me, I want to capture performance, I want to capture cost, I want to capture whatever, right? So, and then as a follow-up question to that, the question is, what data do I need from the pieces in order to be able to conclude that my system has such a property, right? So answering that question usually guides us into how we should define our contracts. But again, so this usually takes a few, conversations about, how we should define locally our contracts. But I say that because it takes work, to define our specifications in such a way that our contract analysis ends up being useful for that application.
Well, I'll follow up then.
Okay, well, let's thank our speaker again.
Related to
You went to the restaurant that you recommended. Wasn't it? Oh, good.
He's the one who told us about that restaurant. We went twice. Did you stay close to the restaurant?
It's close, but like we took the subway, so it was.
There's a reservation. Yeah.
Okay. Tell you the way which we have handled right now, in situations like that, are this. So first of all, a contract itself, classification that we have.
How do you like this?
Oh, I like
As it's an output that corresponds to some of its properties. For example, with my total harmonic distortion that we get from the output, but something that we get to measure, right, from that component. Or it can tell you probability when you do certain things. before for the car. We have added specifications about statistics. Is by computing probability of satisfaction of properties in the input and outputs. So we say this is the probability that the car is going to be safe. Now the question is, how do you know that? Well, you have your own statistical analysis.
A number of possible products.
Exactly. So it is either part of your assumption that we would say, you know,
So this is kind of what I'm getting at.
Yes.
It seems like, you know, I was just curious if there are cases you run into where
I mean, beyond.
okay, this is what I really want. I need to somehow. I guess in some sense an academic question. You're going the other way, starting contracts.
I mean, the question makes it's very relevant. I think that in general, the way which I would try to address something like that is by, instead of generating an infinite set of contracts, I would add to the contract a new set of input variables that control the behavior.
Oh, I see. Okay, all right. So. We just expand your notion of what the contract is to.
That would be my first attempt. And of course, the final test of the contract is whether it is useful. So that's what I was trying to appeal to you, you know, when we spoke about these notions of, you know, question one, system level, question two. What are the test would be, if we define a contract like that, can we, that we are interested in. But that, I mean, I also want to stress the fact that in every single application that we have addressed up to this point, you know, we have had conversations about what classes be used for these applications, and that takes, you know,
Yeah, I can see.
that's in
I
itself
can
a
see
research.
that
That's a research problem.
Because you have situations where you can have exactly the same behavior, but there's like a minimal number of contracts that are actually necessary to bring it about. Help with behavior or whatever. Set some contracts that both give you the same result. And then with ideas like minimal realizations, how few contracts do you need to be a given desired?
Lovely.
To talk about power things.
Oh, yeah, absolutely. Yeah, definitely. Yeah, I'll follow up. I've worked in departments, so I've been completely swamped for the last month, but I'll follow up at some point.
But the university.
Yeah, I just,
And we can fix that by making the assumptions less strict. Or we can fix it by.
anytime you want to talk about that,
More
other
strict.
thing, guidance,
Oh, yeah.
It's really not change. It's just changing time. Different. And the costs are okay, because they're going to propagate down the effect. There's this optimization.
Yeah, that would be good. Whatever you want.
Change the benefits to allow you to
Yeah,
have
like it's.
guarantees.
Yeah, it's like
And the question is,
this class.
this something within the.
Well, I don't know.
Or is this like a separate thing with those costs, like build it on top of this?
Some of the classes.
Does that make sense?
There was complaining about some assumptions. So we realized that the complaint for the one way to simple assumption instead of the more strong assumption. And we're like, what? This makes sense. Please complain for that.
The first thing that comes to my mind is that, you know, I have this.
Some other people that
Yeah.
they're paying for the doing the assumptions. Their neighbors, well, I don't know the reviews that they receive, but they pay are very well hired.
There's some combination. Across all of these that was at minimal cost allowed this change. And you might have some information about.
Yeah, I got six too.
estimated costs of these.
Yeah, I got
But
six,
now
because
you're-
use they were like from the same person.
Lots of its contacts. You'd have something.
Yeah, because you did it.
Search.
Same structure, 1, 2, 3, 4, and the same companies.
Suppose that there is some sort of notion of cost
Could be.
that I want to minimize, that involves variable A.
Yeah, it was in.
Then
Yeah, 65.
I see I plus one equals n. Then the optimization problem would be the composition of C1 all the way to Cn, refining some sort of level specification. What they're saying is that, you know, I want to make sure that I am always satisfying some sort of level specification. But I am.
I mean, I need to complain on you
We are
because I'm
doing
saying
this,
the main complaint was this
you know,
assumption.
we are using the contracts as a feasible set.
I can have it.
Experience, I have told him. To experience, to go on.
It's a bit like strange because like it's funny working cash flow. Australians, so
Yeah, been
so what is my upgraded system?
My students have been calculations now.
How are you going?
I'm thinking maybe to go
Different.
Yeah, we'll go maybe to some friends also that I have in Colorado mine. Yeah,
You know, when am I talking
to
about
see them also.
versus I am talking about different components that I am interconnecting. So in the second case, you are going to use composition. Okay, of contracts. So composition is about going from pieces.
So close to rock pieces.
I'm thinking maybe you're not
It's about I have specifications for the same object that talk about different aspects. For example, I have a specification that talks about functionality, another one about power, and so on. And that is the situation that you. This is power, this is functionality, and so on. And what I want is a single contract that talks about the entire. The same object.
Can I view the different aspect? As some system of this also it's just one of very strict or form of application for different viewpoints or different components here to identify which I should use for change.
The way that I would put that is that if you are talking about specifications that pertain to the same design elements, you are going to be using. You are using contracts that represent different objects that you are interconnecting. You will use composition.
For object with different viewpoints, are these two different viewpoints still represented as different contracts or?
Yes. So a viewpoint is a contract.
Since I think I'm confused, like, now find a difference between this and this. Like, I can know it's from the intuitive idea, but I just cannot have like a very strict definition, like how to differentiate about the viewpoint or.
Okay, okay.
Yeah, you Singapore.
Is the difference between interconnecting components to build a system and having multiple aspects of the same object. Is that something that we can agree on? That, you know, as a,
Yeah, and from high level here into, like, yes, I think, yeah.
okay. So, in your block diagrams, if what we are saying is, I have an interconnection of objects here. Okay, and I am building a system by interconnecting these objects. And I have a contract for this guy, I need to do a contract for this one, then composition is going to be the one that gives us the system level specification.
Yeah.
Because they are different parts. The thing about viewpoints is that I have a processor, and this processor has a contract for power, a contract for timing, a contract for functionality. So merging is the one that in this case gives us the contract for that object. So the difference is between I am interconnecting pieces to build a system, or I am providing multiple contracts that pertain the same design element.
For example, I can buy system. System. But I mean, for, let's say for a system, can we change? Energy or something has different viewpoints, why cannot we build those things as viewpoints instead? I mean, yeah, especially we're doing them as subsystem instead of. Some of the buildings instead of. I think it's different.
Going to provide a more mathematical definition. If you want the guarantees of one component to help you satisfy the assumption of another component, then you have to cover. The only way in which we can do this by merging is not going to help you. So that would be one. You know, so for example, if you have a whole bunch of parallel components, even if you are building a system, and they do not help each other in the sense that they are not interconnected, like you have inputs going to outputs and it's all parallel, the operation of merging and the operation of composition are going to be the same.
From the let's say, because you are using the canonical form, I think for compensation is supposed to be for merging. It's the dual, yeah, it's the dual. I mean, this part is different. Merging, but I think from the functionality.
If you look at packaging, it's the same answer.
Another, I think it's pretty interesting thing is like, it's easy to go from the verbal constraints or, you have the, let's say, any expression to the stats. But I think it's quite challenging to summarize from the stat to a verbal or math expression. How do you achieve that? It's like if you want to it's pretty easy to turn into a stat. You're giving a stat to how to summarize.
Really see much of a difference between it because the way in which you computationally represent sense by some syntactic expression. So back operates on the syntax in order to separate these operations. It is one to one. It is one to one.
Thank you.
How broad are we talking about?
So there's so much I'm meeting right now, but we are meeting soon. Exactly. So before you, is it okay? Okay.
Yeah.
No problem. Please write that down. Want to send an email?
Is there any ways you're able to use the quotient to find assumptions that are violated? Is there any way to generate like a maximal guarantee? Like, say we have some bound of inputs, can we generate like a maximum or bounded on the output directly from the set of contracts going out like for money?
Because we have 8 binary operations. The one that I think is going to give you that is going to be separation.
Okay, and then my other question was practically, what's the computational complexity look like in like how many variables?
That's another question. That's great. Didn't say anything about that. So it depends on.
I know the worst is.
Exactly. Facti was built to be fast.
Okay.
Facti is polynomial most of the time. And then there are some, if some of the polynomial techniques don't work, then it recurs to something that is exponential, but most of the time it's going to be like and that's what enabled the JPL example to run in a minute.
Okay, what roughly number of variables did you guys try this on for?
About 200. No, I remember the number of variables, but they were nice.
Okay, thank you.
You will do this on Tuesday.
I think so. Yes, yeah. It's in the calendar. So I'm sorry.
How do you answer already? You want to see at least the questions? Yeah, we start.